Variable speed can save energy at part load, but the goal is not the lowest speed command. The goal is the lowest safe, stable speed that still delivers the required duty. Every project has an operating terrain containing useful regions, minimum boundaries, and speeds that should be avoided. Begin with demand. Occupancy, process state, temperature, pressure, air quality requirements, and filter loading change throughout the day. If demand is constant near design duty, variable speed has less opportunity. If the system spends long periods at reduced demand, the part load opportunity becomes much more important. Fan laws explain the direction. Under valid similarity conditions, airflow follows speed, pressure follows speed squared, and fan power approximately follows speed cubed. At 80% speed, that suggests 80% flow, 64% pressure, and about 51% idealized fan power, not necessarily electrical input at the meter. These are real Longwell source hardware images, a fan from a variable frequency product photo set, and an open 0 to 10 volt controller. They prove physical context only. Appearance cannot establish the required duty, energy saving, signal mapping, wiring function, or safe operating range for a project. Changing speed moves the fan curve. The system curve then selects the operating point at each speed. The point is not chosen by the speed percentage alone. Dampers, filters, coils, duct geometry, and process openings can reshape the system curve and move the delivered airflow and pressure. Throttling and speed control can reach a similar lower flow through different energy paths. A damper adds resistance, so the fan may generate pressure that the system discards. Speed control reduces the fan curve itself, often lowering both flow and pressure generation. Measure the installed result rather than assuming ideal behavior. A stable control loop connects sensor, setpoint, controller, speed command, air system, and feedback. Sensor location must represent the controlled variable. Setpoint, deadband, gain, and ramp limits need enough authority to respond, but not so much that the fan chases noise or another controller. Minimum speed comes from the application. Outdoor air ventilation, process capture, motor or electronics cooling, minimum duct pressure, damper authority, and sensor validity may all impose a floor. A 0% command is not automatically a valid minimum, and some products define a separate stop state. Now mark exclusion bands. Mechanical resonance, structure vibration, tonal noise, motor temperature, and unstable aerodynamic regions may occur only within certain speeds. The controller should pass through these regions using an approved ramp rather than dwell there. Exact limits require project testing and product documentation. Watch for hunting, repeated speed, and pressure oscillation around the setpoint. Common causes include no deadband, excessive gain, a sensor in turbulent air, long duct delay, conflicting loops, and unrecorded manual overrides. Hunting wastes control effort, creates noise, and can accelerate mechanical wear. Commission every important part load bin, minimum safe point, intermediate demand, and design duty. At each bin, measure airflow, pressure, electrical input, current, vibration, sound, command, and feedback. Confirm duty, limits, and stability together. A low instantaneous kilowatt reading is not enough if airflow or control is unacceptable. Release a usable control envelope containing the demand profile, system curve, fan curves by speed, minimum safe speed, exclusion bands, sensor location, setpoint schedule, deadband, ramp limits, alarms, fallback state, and commissioning records. That package turns variable speed from a feature into a controlled operating strategy. For a project-specific control envelope review, contact Longwell.